Tonight, we're exploring one of the most fundamental questions humans have ever asked. Where does the universe end? Is there a boundary somewhere out there? A cosmic wall we could run into? Or does space simply continue forever, with no edge at all? The answer is stranger and more subtle than you might expect, and it will completely change how you think about reality itself. If you enjoy these explorations, a like or subscribe really helps this channel grow. Now, let's begin. Every object you've ever encountered has boundaries. A room has walls. An ocean has shores. A box has sides. Your own body has skin that separates you from the world around you. Boundaries are everywhere in our daily experience. So naturally, when ancient peoples looked up at the night sky, they wondered, where does all of this end? The Babylonians, around 3,000 years ago, had a straightforward answer. They believed Earth was a flat disk surrounded by a cosmic ocean. Above this ocean stretched a solid dome, the firmament, which held back the waters of chaos from flooding the world below. The stars were holes punched in this dome, allowing divine light to shine through. It was a tidy cosmology, where everything had its place and clear boundaries separated the mortal realm from the heavens. This wasn't just religious mythology. It was their best attempt to explain observations with the tools they had. The sky does appear as a dome overhead. Stars do seem fixed to a surface. The sun and moon do appear to move across this dome. Without telescopes, mathematics, or physics, their model made sense of what they could see. The ancient Egyptians had their own version, imagining the sky as a goddess named Nut, whose body arched over the earth. Ancient Hindus described the earth resting on elephants, standing on a turtle, which itself stood on a cosmic serpent. These models varied in details, but shared common themes. The universe was comprehensible, bounded, and relatively small. Ancient Greece brought geometric sophistication to cosmology. Around 350 BC, Aristotle constructed an elegant model where Earth sat motionless at the center, while crystalline spheres rotated around it. Each transparent sphere carried a celestial object, the moon on the innermost sphere, then Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the sphere of fixed stars. Beyond that outermost sphere, Aristotle claimed, there was nothing. Not empty space, but literally no existence of any kind. The concept of beyond simply didn't apply. This model had real, explanatory power. It predicted planetary motions reasonably well. It explained why stars appeared fixed while planets wandered across the sky. It fit with Aristotle's physics, where every object had a natural place and motion. Heavy elements fell toward Earth at the center. Light elements rose toward the heavens. Celestial objects moved in perfect circles because circles were the most perfect geometric shape, befitting the perfect heavens. The Aristotelian cosmos dominated Western thought for nearly 2,000 years. In the 2nd century AD, the astronomer Ptolemy refined it by adding epicycles, small circles on top of the larger circular orbits to better match detailed observations. This Ptolemaic system could predict planetary positions with impressive accuracy for ancient astronomy, good enough to create calendars and navigate by the stars. But a Greek philosopher named Archytas had posed a question that would haunt this neat picture. Imagine you travel to the edge of Aristotle's universe, to that outermost sphere of stars. Now, stick your hand out past the edge. What happens? If something physical blocks your hand, then that something must be part of the universe too. So the supposed edge wasn't actually the edge. But if nothing blocks your hand, if it passes through freely, then space must continue beyond a boundary. Either way, you haven't found a true edge. you've just redefined where you think the edge is. This paradox cuts deep. It reveals that our intuitions about edges come from living among objects within space. Tables have edges, countries have borders, but space itself is not an object. It's the arena, the stage on which everything exists. What would it even mean for the stage itself to have an edge? Where would the edge be? In what would it exist? Medieval scholars wrestled with Archytas's paradox. Some argued that beyond the sphere of stars lay absolute nothingness. But this raised impossible questions. Can nothing exist? If there's truly no space beyond the stars, no dimension, no extent, how can we even meaningfully discuss what's beyond? The very act of saying, beyond the edge there is nothing, seems to imply there's a beyond, a place where this nothing is located. The concept devours itself. Other medieval thinkers took a different approach, appealing to theology. They suggested that God existed beyond the physical universe, and God's infinite nature meant that in some sense, space continued infinitely, not as physical space, but as the infinite extent of divine presence. This solved the philosophical problem by moving it into the realm of theology, but it sidestepped the physical question. What is the actual nature of space? Does it have boundaries? The scientific revolution of the 1600s and 1700s shattered these ancient certainties. When Galileo Galilei turned one of the first telescopes skyward in 1610, he saw things that contradicted Aristotelian cosmology. The moon had mountains and craters, not the perfect smooth sphere Aristotle described. The sun had dark spots that appeared and moved, showing the heavens were not perfect and unchanging. Most dramatically, he discovered 4 moons orbiting Jupiter, proving that not everything in the cosmos orbited Earth. These observations were revolutionary because they showed the heavens were made of ordinary matter governed by the same laws as Earth. There were no perfect crystalline spheres. The celestial realm was not fundamentally different from the terrestrial realm. By the late 1600s, Isaac Newton had developed a comprehensive physics based on universal gravitation and 3 laws of motion. In Newton's view, space was absolute and infinite, extending forever in all directions like an infinite stage. Every object in this space attracted every other object through gravity, with the force depending on their masses and the distance between them. This was a radical departure from the bounded Aristotelian universe. Newton's space had no center and no edge. It was uniform and infinite, but this raised a new puzzle. If space is infinite and contains matter distributed throughout, wouldn't gravity pull all the matter together into one massive clump at some center? Newton recognized this problem, but didn't have a good solution. He suggested that God might occasionally intervene to keep things properly distributed, but this didn't satisfy everyone. The question had evolved. It was no longer about crystalline spheres and cosmic domes. It was about the fundamental nature of space itself. Is it truly infinite? If so, how can the universe be stable? If not, where are its boundaries and what lies beyond? By the 19th century, astronomers were beginning to measure the universe. The key was developing techniques to determine cosmic distances, building what's now called the cosmic distance ladder, where each measurement method builds on the previous one. The first rung was parallax. Hold your finger at arm's length and look at it with one eye, then the other. Your finger appears to shift position against the background. That's parallax. The closer your finger is, the larger the shift. Stars show parallax too. As Earth orbits the Sun, our viewing position changes by about 300 million kilometers over 6 months. Nearby stars appear to shift position slightly against the background of much more distant stars. Measure this shift. and you can calculate the star's distance using simple geometry. But the shifts are tiny. Even the nearest stars show parallax of less than 1 arcsecond. An arcsecond is 1/3600th of a degree. Imagine dividing a degree into 3,600 slices. That's how precisely astronomers needed to measure. It wasn't until 1838 that Friedrich Bessel successfully measured the parallax of a star called 61 Cygni. The parallax was about 0.314 arcseconds, placing the star about 11 light-years away. This was a breakthrough. It proved stars were at vast distances, far beyond anything in our solar system. But parallax only works for nearby stars. Beyond a few thousand light-years, the shifts become too small to measure even with modern telescopes. The European Space Agency's Gaia satellite, launched in 2013, has measured parallaxes for over 1 billion stars with unprecedented precision. This has created a three-dimensional map of our galaxy, revealing its structure in detail. But even Gaia can only measure parallax reliably out to about 30,000 light-years. For greater distances, we need other methods. The next rung came in the early 1900s, when Henrietta Swan-Leavitt, working at Harvard College Observatory, discovered a crucial relationship. She studied variable stars called Cepheids that brighten and dim in a regular cycle. Leavitt found that brighter Cepheids have longer periods. A Cepheid that takes 10 days to complete one cycle is intrinsically brighter than one that takes 5 days. This was revolutionary. By measuring a Cepheid's period, you could determine its true brightness. Then, by comparing its true brightness to how bright it appears from Earth, you could calculate its distance. It's like seeing a light bulb in the distance. If you know it's a 100-watt bulb, you can estimate how far away it is by how bright it looks. Leavitt discovered this relationship by studying Cepheids in the Small Magellanic Cloud, a dwarf galaxy orbiting the Milky Way. Since all the Cepheids in the Small Magellanic Cloud are roughly the same distance from us, differences in their apparent brightness reflect differences in their true brightness. By plotting their periods against their apparent magnitudes, she found a clear relationship. The discovery was published in 1912 and fundamentally changed astronomy. Cepheids are bright enough to be seen in distant galaxies, giving astronomers a way to measure distances across millions of light-years. Edwin Hubble used this method in the 1920s to measure the distance to the Andromeda Galaxy, proving it was far beyond our Milky Way and establishing that the universe contained many separate galaxies. For even greater distances, astronomers use Type Ia supernovae. These are exploding white dwarf stars that always reach approximately the same peak brightness, making them standard candles visible across billions of light-years. A white dwarf in a binary system can pull matter from its companion star. When the white dwarf's mass reaches about 1.4 times the Sun's mass, called the Chandrasekhar limit, it becomes unstable and explodes. Because Type Ia supernovae always explode at the same mass, they always release the same amount of energy and reach the same peak brightness. By measuring how bright a Type Ia supernova appears, astronomers can calculate its distance. These explosions are so bright they can be seen halfway across the observable universe. The use of Type Ia supernovae led to the discovery of dark energy in 1998. By measuring supernovae at different distances and therefore different times in cosmic history, astronomers could track how the expansion rate has changed over billions of years. They expected to find that gravity had been slowing the expansion. Instead, they found it accelerating. Each rung of this cosmic distance ladder extends our reach farther. Parallax gives distances to nearby stars out to a few thousand light-years. Those measurements calibrate the Cepheid relationship, extending our reach to tens of millions of light-years. Cepheids give distances to nearby galaxies, which help calibrate the supernova method. Supernovae give distances across billions of light-years, reaching back in time to when the universe was less than half its current age. This carefully constructed ladder, where each method calibrates the next, is how we know the universe is as large as it is. Each step must be calibrated precisely because errors propagate up the ladder. A 10% error in the Cepheid distance scale becomes a 10% error in the supernova distance scale. Astronomers spend enormous effort refining each step to minimize these errors. In the early 20th century, astronomers faced a fundamental question. Are there other galaxies beyond the Milky Way, or is the Milky Way the entire universe? Through telescopes, astronomers could see fuzzy patches of light called nebulae. Some were clearly clouds of gas within our galaxy, like the Orion Nebula. But others, called spiral nebulae because of their distinctive pinwheel shape, were mysterious. Were they nearby gas clouds rotating within the Milky Way? Or were they island universes, separate galaxies far beyond our own? Different astronomers had different opinions. And the question was urgent because it determined the fundamental nature and size of the universe. If spiral nebulae were part of the Milky Way, then the Milky Way was the entire universe, perhaps a few 100,000 light-years across. If spiral nebulae were separate galaxies, then the universe was vastly larger, containing innumerable galaxies scattered across billions of light-years. In 1920, this question came to a head in what's now called the Great Debate, held at the Smithsonian Museum of Natural History in Washington. Astronomers Harlow Shapley from Mount Wilson Observatory and Heber Curtis from Lick Observatory presented opposing views before the National Academy of Sciences. Shapley argued that spiral nebulae were relatively small objects within the Milky Way. He pointed to observations suggesting the Milky Way was very large, perhaps 300,000 light-years across, large enough to contain these spirals. He also noted that if spiral nebulae were external galaxies, they'd have to be extraordinarily distant and enormous to appear as bright as they do. Curtis argued that spiral nebulae were separate galaxies. He pointed to the fact that novae, exploding stars, appeared much dimmer in spiral nebulae than in our galaxy, suggesting they were much farther away. He also noted that some spiral nebulae showed dark dust lanes, similar to what we'd expect if they were disk-shaped systems of stars viewed edge-on, like galaxies. Both astronomers made valid points, and neither could definitively prove their case. The debate couldn't be settled by argument alone. Someone needed to measure the actual distance to a spiral nebula. If that distance was clearly beyond the boundaries of the Milky Way, Curtis would be vindicated. If the distance was small enough to place the nebula within the Milky Way, Shapley would be right. That crucial measurement came from Edwin Hubble in 1923 and 1924. Using the 100-inch Hooker telescope at Mount Wilson Observatory, then the largest telescope in the world, Hubble identified Cepheid variable stars in the Andromeda Nebula. These stars brightened and dimmed with regular periods, and Hubble could measure those periods precisely. Using Henrietta Leavitt's period luminosity relationship, Hubble calculated that Andromeda was about 900,000 light-years away. This was far beyond the known extent of the Milky Way, which was estimated at about 100,000 light-years across at the time. Andromeda was not a nebula within our galaxy. It was a separate galaxy. Hubble announced his results in 1924, and they were decisive. If Andromeda was a galaxy, then many other spiral nebulae must be galaxies too. The universe was not just the Milky Way. It was a vast expanse filled with countless galaxies, each containing billions of stars. This discovery was as revolutionary as Copernicus's claim that Earth orbits the Sun. It decentralized us again. We were not at the center of the solar system. The solar system was not at the center of the galaxy. And now, the Milky Way was not the center or extent of the universe. It was one galaxy among billions, perhaps trillions. Shapley had been wrong about spiral nebulae being within the Milky Way, but he'd been right that the Milky Way was larger than previously thought. Later measurements refined the distance to Andromeda to about 2.5 million light-years, and the Milky Way's diameter to about 100,000 light-years, close to what Shapley had suggested. The Great Debate represents a turning point in astronomy, the moment when we realized the universe was vastly larger than anyone had imagined, filled with galaxies beyond counting, each a collection of billions of stars, many with planets scattered across billions of light-years of space. Before going further, we need precision about terminology. The word universe comes from Latin, meaning everything that exists. That's our definition. The universe is everything. All space, all time, all matter, all energy, everything that exists, anywhere, at any time. But modern cosmology requires a crucial distinction. There's the universe, meaning everything that exists, and then there's the observable universe, meaning the part we can actually see from Earth. The observable universe is limited by two facts. Light travels at finite speed, and the universe has a finite age. Light moves at about 300,000 kilometers per second, fast but not infinite. In the 13.8 billion years since the Big Bang, light has only had 13.8 billion years to travel, but space itself has been expanding during this time. An object that emitted light toward us 13.8 billion years ago was much closer back then. While that ancient light traveled toward us, expansion carried the object farther away. By the time the light reaches us, that object is now about 46.5 billion light-years away. This defines the observable universe, a sphere centered on Earth with a radius of about 46.5 billion light-years. Everything within this sphere is potentially observable. Everything beyond it is not, at least not yet. The observable universe contains about 2 trillion galaxies. Each galaxy has hundreds of billions of stars on average. Many of those stars have planets. The total number of planets in the observable universe is estimated at 100 billion trillion or more. That's the number 1 followed by 23 zeros. But the observable universe is almost certainly not the entire universe. It's just our view, limited by how far light has had time to reach us. The whole universe is likely vastly larger, possibly infinite. We'll never see most of it. Think of standing on a ship in the middle of the ocean on a clear day. You can see to the horizon maybe 20 kilometers in every direction. That defines your visible ocean, a circle 40 kilometers across centered on you. But the ocean extends far beyond your horizon. The Pacific Ocean is tens of thousands of kilometers across. Your visible patch is tiny compared to the whole. The observable universe is similar. It's our visible patch of a much larger whole. Move to a different location in the universe, and you'd see a different patch centered on your new position. Here's something subtle about the observable universe that's crucial to understand. It's different for every observer. If intelligent beings existed in a galaxy 40 billion light-years from Earth, they'd have their own observable universe, a sphere centered on them extending 46.5 billion light-years in every direction from their location. Some of what they observe would overlap with what we observe. a galaxy located 20 billion light-years from both Earth, and their location would be visible to both civilizations. Both of us could study it, measure it, observe it, but they'd also see billions of galaxies we can never observe. Galaxies 60 or 70 billion light-years from Earth are beyond our horizon. Their light hasn't had time to reach us. But some of those galaxies might be only 30 billion light-years from our hypothetical alien astronomers. They'd see them clearly, study their properties, include them in their maps of the cosmos. And the reverse is true. We see galaxies they can never observe. Galaxies in regions of space that are beyond their horizon, but within ours. The observable universe isn't a thing. It's not an object or a structure. It's a description of what one particular observer can see from one particular location at one particular time. Change your location, and the boundary changes. The horizon moves with you. Imagine standing in fog on a perfectly flat field. You can see clearly for maybe 100 meters in all directions. Beyond that, fog obscures everything. There's a circle of visibility around you. Now walk forward. That circle moves with you. You're always at its center. You never get closer to the edge of visibility because it's not a fixed edge. It's just the limit of how far you can see from wherever you happen to be standing. The observable universe works the same way. It's not a boundary in space that you could travel toward. It's the limit of your view from your current position. Move your position, and the limit moves with you. You're always at the center of your own observable universe, just as everyone else is at the center of theirs. This means asking what's at the edge of the observable universe is like asking what's at the horizon of the ocean. The horizon isn't a place. It's just where your view ends. Someone standing somewhere else has a different horizon. There's no special location in the ocean that is the horizon. The horizon is relative to the observer. So what exists beyond the observable universe, in regions so distant that their light hasn't reached us yet? We can't observe it directly by definition, but we can make educated inferences. When astronomers map the observable universe, they find something remarkable. It looks essentially the same in every direction. This property is called isotropy. Point a telescope north, and you see a certain density of galaxies, certain types of structures, certain distributions of matter. Point it south, east, west, up, down, and after averaging over sufficiently large volumes, you see the same thing. The universe has no preferred direction. This has been measured very carefully. Astronomers have divided the sky into millions of small patches and counted galaxies in each patch. They've measured galaxy brightnesses, colors, distances, velocities. The result is clear. The universe is isotropic to high precision. Some patches have slightly more galaxies, some slightly fewer. But these variations are small and follow statistical patterns consistent with random fluctuations. On average, the universe looks the same in all directions. Isotropy alone is interesting, but it could still be consistent with Earth being in a special location. Maybe we're at the center of a spherical distribution of galaxies. From the center, everything would look the same in all directions, but from other locations, it would look different. But there's no reason to think Earth is in a special location. We're not at the center of the solar system. The sun is. We're not at the center of the galaxy. We're about halfway out in a spiral arm. There's no indication that our galaxy is at the center of anything either. Copernicus taught us nearly 500 years ago that we're not at the center of the cosmos. This leads to the cosmological principle. The universe is both isotropic and homogeneous. Isotropic means it looks the same in all directions from any particular location. Homogeneous means it has the same properties at every location. Put simply, the universe is pretty much the same everywhere when you average over large enough scales. If the cosmological principle is true, then what we observe from Earth is representative of the whole universe. The observable universe is a fair sample, and this means that beyond our horizon, there are simply more galaxies, more stars, more planets, just more of the same, extending outward. But how far does it extend? Does it go on forever, or is there an endpoint? Einstein's general theory of relativity, published in 1915, revolutionized our understanding of space, time, and gravity. In Einstein's theory, space and time are not separate entities. They're woven together into a four-dimensional fabric called space-time. Matter and energy curve this fabric, and objects follow the curvature, which we perceive as gravity. On a local scale, this explains why objects fall toward Earth. Earth's mass curves space-time around it, and objects follow geodesics, the straightest possible paths through curved space-time, which from our perspective appear as falling. But general relativity also describes the global structure of the universe. The total amount of matter and energy in the universe determines its large-scale geometry. Three possibilities exist. If the universe contains enough matter and energy, specifically more than a critical density, space curves back on itself like the surface of a sphere. This is called a closed universe. It would be finite in total volume, but have no edge or boundary. Just as you can walk around Earth's surface forever without reaching an edge or falling off, you could travel through a closed universe forever and never encounter a boundary. Travel far enough in one straight line, and you'd eventually return to your starting point from the opposite direction, having circumnavigated the universe. If the universe contains less than the critical density, space curves the opposite way, with a saddle-like geometry. This is called an open universe. It would be infinite, extending forever in all directions with no edge. If the universe contains exactly the critical density, space is perfectly flat, with zero curvature. This flat universe would also be infinite. So, the answer to whether the universe is finite or infinite depends on its geometry, which depends on its total matter and energy content. How do we measure this? The primary method is examining the cosmic microwave background, the oldest light in the universe. About 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. Before this, the universe was filled with hot plasma, where electrons and nuclei were separated. Photons couldn't travel far before scattering off free electrons. The universe was opaque. But when atoms formed, electrons bound to nuclei, and suddenly photons could travel freely. The universe became transparent. The light from this moment has been traveling through space ever since, stretched and cooled by cosmic expansion. Today it appears as microwave radiation with a temperature of about 2.7 degrees above absolute zero. This cosmic microwave background has tiny temperature variations, typically only about 1 part in 100,000. These variations represent density fluctuations in the early universe, the seeds that grew into galaxies and galaxy clusters. The pattern of these temperature variations depends on the curvature of space. If space curves like a sphere, the hot and cold spots appear larger than they would in flat space. If space curves like a saddle, they appear smaller. By measuring the angular size of these spots very precisely, scientists can determine the universe's curvature. Multiple satellites have mapped the cosmic microwave background in increasing detail. The Cosmic Background Explorer in the 1990s confirmed its existence and temperature. The Wilkinson microwave anisotropy probe in the 2000s mapped the temperature variations. The Planck satellite, operational from 2009 to 2013, produced the most detailed maps yet. The primary method is examining the cosmic microwave background, the oldest light in the universe. About 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. Before this, the universe was filled with hot plasma, where electrons and nuclei were separated. Photons couldn't travel far before scattering off free electrons. The universe was opaque. But when atoms formed, electrons bound to nuclei, and suddenly photons could travel freely, the universe became transparent. The light from this moment has been traveling through space ever since, stretched and cooled by cosmic expansion. Today, it appears as microwave radiation with a temperature of about 2.7 degrees above absolute zero. This cosmic microwave background has tiny temperature variations, typically only about 1 part in 100,000. These variations represent density fluctuations in the early universe, the seeds that grew into galaxies and galaxy clusters. The pattern of these temperature variations depends on the curvature of space. If space curves like a sphere, the hot and cold spots appear larger than they would in flat space. If space curves like a saddle, they appear smaller. By measuring the angular size of these spots very precisely, scientists can determine the universe's curvature. Multiple satellites have mapped the cosmic microwave background in increasing detail. The Cosmic Background Explorer in the 1990s confirmed its existence and temperature. The Wilkinson microwave anisotropy probe in the 2000s mapped the temperature variations. The Planck satellite, operational from 2009 to 2013, produced the most detailed maps yet. The result from Planck: the universe is flat to within about 0.4%. Either the universe has zero curvature and is infinite, or any curvature is so slight we can't detect it with current measurements. But there's an important caveat. These measurements probe the observable universe and somewhat beyond, but they can't tell us about the entire universe if it's much larger than what we can see. Imagine measuring Earth's curvature by examining a 10-meter patch of ground. You'd find it appears perfectly flat. You'd need to survey a much larger area, hundreds of kilometers, to detect Earth's curvature. Similarly, the observable universe might be a tiny patch of a much larger curved space. If the whole universe is a sphere with a circumference of trillions of light years, we'd only see a tiny fraction, and it would appear flat to us. So we can't be completely certain whether the universe is finite or infinite. The simplest interpretation of the measurements is that it's flat and infinite. But a very large finite universe that appears flat at observable scales remains possible. In 1929, Edwin Hubble made what might be the most important astronomical discovery of the 20th century. He'd been measuring the velocities of galaxies by examining their light. When an object moves away from you, its light shifts toward longer wavelengths, toward the red end of the spectrum. This is called redshift, analogous to how an ambulance siren drops in pitch as it drives away. Hubble found that nearly all galaxies showed redshift, meaning they were moving away from us. But more than that, he discovered a relationship. The farther away a galaxy was, the faster it was receding. Galaxies twice as far away were moving away twice as fast. Galaxies 3 times as far were moving 3 times as fast. Distance and velocity were proportional. This relationship, now called Hubble's law, had a profound implication. It wasn't that galaxies were flying through space away from the Milky Way, as if we were at the center of some explosion. Rather, space itself was expanding, carrying galaxies along with it. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot. From any dot's perspective, all the other dots appear to be moving away, with farther dots moving faster. But the dots aren't moving across the balloon's surface. The surface itself is stretching between them. The universe works the same way in 3 dimensions. Every region of space is expanding. Galaxies that are farther apart have more expanding space between them, so they separate faster. This expansion isn't happening in space. It's an expansion of space itself. This discovery shocked the scientific community. Even Einstein hadn't believed the universe could be expanding. His equations of general relativity had actually predicted either expansion or contraction, but Einstein thought the universe must be static, neither growing nor shrinking. He'd modified his equations by adding a term called the cosmological constant, specifically to hold the universe static against gravitational collapse. When Hubble's observations proved the universe was expanding, Einstein realized his modification had been unnecessary. He reportedly called it his greatest blunder, though this quote may be apocryphal. Ironically, the cosmological constant would later make a comeback in a different context. Let's dig deeper into how redshift works and what it tells us. Light is an electromagnetic wave with a characteristic wavelength. Red light has longer wavelengths, around 700 nanometers. Blue light has shorter wavelengths, around 400 nanometers. When a source of light moves away from you, the wavelengths get stretched, shifted toward the red end of the spectrum. For nearby objects moving through space, like a receding car or rocket, this is called Doppler shift, the same effect that changes the pitch of an ambulance siren. The siren sounds higher pitched as the ambulance approaches because sound waves are compressed, and lower pitched as it recedes because they're stretched. But for distant galaxies, something more profound happens. The galaxies aren't moving through space as much as space itself is expanding between us and them. The difference is subtle but crucial. Imagine an ant walking on a rubber band. If you stretch the rubber band while the ant is walking, the ant moves relative to the rubber, but the rubber also stretches beneath it. The ant's total displacement is a combination of its motion across the rubber and the stretching of the rubber itself. In the universe, galaxies have some random motion through space, typically a few hundred kilometers per second. This creates standard Doppler shift. But for distant galaxies, the dominant effect is the expansion of space itself, which carries galaxies apart at speeds that increase with distance. When light leaves a distant galaxy, it has some wavelength determined by the atomic transitions that produced it. As that light travels toward us across billions of light years, the space it's traveling through is expanding. This expansion stretches the wavelength of the light itself. By the time the light reaches us, its wavelength has been stretched proportionally to how much space has expanded during the light's journey. Measuring redshift is relatively straightforward. Atoms emit and absorb light at specific wavelengths determined by quantum mechanics. These create spectral lines, like fingerprints for each element. Hydrogen, for example, has a characteristic line at a wavelength of 656.3 nanometers called H-alpha. Calcium has strong lines at 393.4 and 396.8 nanometers called the H and K lines. When we look at light from a distant galaxy, we see these same spectral lines but shifted toward longer wavelengths. If we see the H-alpha line at 984.4 nanometers instead of 656.3 nanometers, we know the wavelength has been stretched by exactly 50%. Redshift is expressed as a dimensionless number z, defined as the fractional change in wavelength. In the example above, Z equals 0.5. A redshift of Z equals 1 means wavelengths have doubled. A redshift of Z equals 2 means wavelengths have tripled. The most distant galaxies observed by the James Webb Space Telescope have redshifts above Z equals 13, meaning their wavelengths have been stretched by a factor of 14. From redshift, astronomers can calculate how much the universe has expanded since the light was emitted. A redshift of Z equals 1 means the universe has doubled in size. A redshift of Z equals 3 means it's quadrupled in size. This tells us about cosmic history and the expansion rate at different times. Using Hubble's law, which relates redshift to distance, we can calculate how far away the galaxy is. For nearby galaxies, the relationship is simple and linear. For distant galaxies, it becomes more complicated because the expansion rate has changed over cosmic history, affected by the relative amounts of matter and dark energy. Combining redshift with the speed of light, we can also calculate how long ago the light was emitted, giving us a look-back time. Light from a galaxy at redshift Z equals 1 was emitted about 7.7 billion years ago, when the universe was about 6 billion years old. Light from a galaxy at redshift Z equals 6 was emitted about 12.8 billion years ago, when the universe was less than a billion years old. This means high redshift galaxies show us the universe in its youth. The James Webb Space Telescope is designed specifically to observe these distant, redshifted galaxies, revealing how the first stars and galaxies formed. It detects infrared light, which is crucial because the visible light from early galaxies has been redshifted into the infrared part of the spectrum. The highest redshift quasar ever detected has a redshift of about 7.6, showing us a supermassive black hole that existed when the universe was only 670 million years old. The light we see from it today was emitted 13.1 billion years ago and has been traveling toward us across the expanding universe ever since. If the universe is expanding now, it was smaller in the past. This is inescapable. Rewind time, and galaxies were closer together. The universe was denser and hotter. Go back far enough, and all the matter and energy in the observable universe was compressed into a smaller and smaller volume. Extrapolate to the ultimate past, and you reach a point where all the matter and energy was compressed into an infinitesimally small region of infinite density and temperature. This is the Big Bang, the beginning of the universe as we know it. The name Big Bang was actually coined by Fred Hoyle, a prominent astronomer who didn't believe in it. Hoyle preferred the steady state theory, which held that the universe had always existed and always would exist. In steady-state cosmology, as the universe expands and galaxies move apart, new matter constantly appears in the spaces between them, keeping average density constant. The universe has no beginning and no end. Hoyle used the term Big Bang mockingly in a radio broadcast in 1949, trying to make the idea sound absurd. But the name stuck. And ironically, it's Hoyle's steady-state theory that's been abandoned while Big Bang cosmology has become the foundation of modern cosmology. The Big Bang theory makes specific predictions. If the universe began in a hot, dense state and has been expanding and cooling, there should be remnant heat left over from that early state, cooled by expansion, but still detectable. In 1948, physicists George Gamow, Ralph Alpher, and Robert Herman predicted this cosmic background radiation should have a temperature of about 5 degrees above absolute zero. In 1964, Two physicists at Bell Telephone Laboratories, Arno Penzias and Robert Wilson, were trying to eliminate noise from a sensitive radio antenna. No matter what they did, they detected a persistent signal coming equally from all directions in the sky. They even suspected pigeon droppings in the antenna might be the cause and cleaned it out. The signal remained. Eventually, they learned that physicists at nearby Princeton University had been looking for exactly such a signal. The microwave noise Penzias and Wilson had discovered was the cosmic microwave background, the cooled remnant of radiation from the Big Bang itself. Its temperature was about 3 degrees above absolute zero, remarkably close to the earlier prediction. This discovery was revolutionary. It provided direct evidence for the Big Bang and dealt a fatal blow to the steady-state theory. Penzias and Wilson won the Nobel Prize in Physics in 1978 for their accidental discovery. But what exactly is the cosmic microwave background? When the universe was very young, about 380,000 years after the Big Bang, it was filled with hot plasma. Nuclei and electrons were separated, and photons couldn't travel far before scattering off the free electrons. The universe was opaque, like being inside a glowing fog. But as expansion cooled the plasma, electrons and nuclei combined to form neutral atoms. Suddenly, photons could travel freely across the universe without scattering. The universe became transparent. This moment is called recombination, and the light from this moment has been traveling through space ever since. That light has been stretched by cosmic expansion. Originally emitted as visible and infrared light, it's now stretched into the microwave part of the spectrum. We see it as a faint glow filling the entire sky, with a temperature of 2.725 degrees above absolute zero. The cosmic microwave background isn't perfectly uniform. It has tiny temperature variations, typically about 1 part in 100,000. These variations are incredibly important because they tell us about density fluctuations in the early universe. Regions that were slightly denser than average appear slightly warmer in the cosmic microwave background. Regions that were slightly less dense appear slightly cooler. These density variations were the seeds that grew through gravitational attraction over billions of years into the galaxies and galaxy clusters we see today. Multiple spacecraft have mapped these temperature variations in increasing detail. The Cosmic Background Explorer, launched in 1989, first detected them. The Wilkinson Microwave Anisotropy Probe, operational from 2001 to 2010, produced detailed maps. The Planck satellite, from 2009 to 2013, created the most precise maps yet, measuring temperature variations to parts per million. These maps are treasure troves of information. The pattern of hot and cold spots depends on the composition of the universe, its geometry, and its expansion history. By analyzing the patterns, cosmologists have determined that ordinary matter makes up only about 5% of the universe's total energy content. Dark matter, which we can't see directly but which exerts gravitational effects, makes up about 27%. And dark energy, which drives accelerating expansion, makes up about 68%. The maps also confirm the universe is spatially flat, to high precision, and provide the most accurate measurement of the universe's age, 13.797 billion years, with an uncertainty of only about 20 million years. Despite its success, the Big Bang theory faced puzzles that suggested something important was missing from the picture. Two problems stood out: the horizon problem and the flatness problem. The horizon problem goes like this. When we look at the cosmic microwave background from opposite sides of the sky, we're looking at regions that are now about 90 billion light-years apart. But these regions couldn't have been in contact with each other in the early universe. Light couldn't have traveled between them in the time since the Big Bang, yet they have almost exactly the same temperature, agreeing to 1 part in 100,000. How did they agree to have the same temperature if they've never communicated? It's like finding that every lake on Earth has exactly the same temperature, even though the lakes have never been connected and couldn't have exchanged heat. The flatness problem is equally puzzling. Our measurements show the universe is extraordinarily flat. But flatness is unstable. A universe that's even slightly curved becomes more curved over time as it expands. If the early universe had been just 1 part in 10 to the power of 60 away from perfect flatness, it would have either collapsed back on itself or expanded so fast that structures couldn't form. Yet here we are, 13.8 billion years later, and the universe is still flat to within 0.5%. This requires the early universe to have been flat to absurd precision, fine-tuned to at least 60 decimal places. Why? What set the initial conditions so precisely? In 1980, physicist Alan Guth proposed a radical solution that would revolutionize cosmology. He called it cosmic inflation. The idea is that in the first tiny fraction of a second after the Big Bang, specifically between about 10 to the power of negative 36 seconds and 10 to the power of negative 32 seconds after the beginning, the universe underwent a period of exponential expansion far faster than the normal expansion we see today. During inflation, space doubled in size repeatedly, every minuscule instant. The total expansion was enormous. The universe grew by a factor of at least 10 to the power of 26 in a fraction of a trillionth of a second. To put this in perspective, if an atom inflated by the same factor, it would end up larger than the observable universe. This sounds absurd, but inflation elegantly solves both the horizon and flatness problems. Any initial curvature gets stretched flat, like inflating a balloon, until its surface appears perfectly flat. This explains why the universe is so close to flat today. It was flattened by inflation regardless of what its initial curvature was. Inflation also solves the horizon problem. Before inflation, the entire observable universe was compressed into a tiny region, small enough that all parts were in thermal contact. They reached the same temperature. Then inflation stretched this tiny region enormously, separating parts that had been in contact. They retained their uniform temperature because they'd already been in equilibrium before inflation separated them. Inflation makes specific predictions about the cosmic microwave background. The density fluctuations we see as temperature variations should follow a particular statistical pattern. Inflation predicts they should be nearly scale invariant, meaning the pattern looks similar at different size scales. It also predicts the fluctuations should be Gaussian random, following a specific type of statistical distribution. When the Wilkinson Microwave Anisotropy Probe and Planck satellite measured the cosmic microwave background in detail, they found exactly the predicted patterns. The fluctuations are indeed nearly scale invariant and Gaussian random, matching inflation's predictions remarkably well. Inflation also predicts the existence of gravitational waves from the inflationary period itself. These primordial gravitational waves would leave a specific imprint in the polarization of the cosmic microwave background. Experiments are currently searching for this signal. If found, it would provide direct evidence for inflation and reveal the energy scale at which inflation occurred. Beyond solving problems and matching observations, inflation has another profound implication. It suggests the universe is vastly larger than the observable universe. The observable universe represents just a tiny patch of a much larger whole. Think about it. Inflation expanded space by a factor of at least 10 to the power of 26. The observable universe is the region that's expanded normally since inflation ended. But the entire inflated region is much larger. Even if we could see in all directions infinitely far, we'd still only be seeing a tiny fraction of what inflation created. This means the universe extends far, far beyond what we can observe. How far? Possibly infinitely far. The unobservable universe could be vastly larger than the observable part, perhaps infinite in extent. For decades after discovering cosmic expansion, astronomers assumed gravity must be slowing it down. The mutual gravitational attraction of all matter should act like a brake, gradually decelerating the expansion. The question was whether there's enough matter to eventually halt expansion entirely and cause the universe to recollapse in a big crunch, or whether expansion would continue forever, just slowing down over time. Then in 1998, two independent teams of astronomers studying distant supernovae made a shocking discovery. They were using Type Ia supernovae as standard candles to measure the expansion rate at different times in cosmic history. By comparing nearby supernovae to distant ones, they could see how much the expansion had slowed over billions of years. Instead, they found the expansion is speeding up. Distant supernovae appeared slightly dimmer than expected, indicating they were farther away than they should be if expansion were constant or slowing. The only way to explain this was if expansion had been accelerating. This was so unexpected that both teams initially thought they'd made errors. They checked and rechecked their data. They looked for possible sources of systematic error. They analyzed different samples of supernovae. Every check confirmed the result. The expansion of the universe is accelerating. This discovery earned the team leaders the Nobel Prize in Physics in 2011. It also introduced one of the deepest mysteries in modern physics: dark energy. Dark energy is the name we give to whatever is causing the acceleration, but calling it a name doesn't mean we understand it. We don't know what dark energy is. We just know it exists because we can measure its effects. Dark energy behaves unlike anything we normally encounter. It's not matter or radiation. It doesn't clump or cluster. It's spread uniformly throughout space. Every cubic meter of space contains the same amount of dark energy, whether that space is inside a galaxy, between galaxies, or in the vast cosmic voids. This uniform distribution has a strange consequence. As the universe expands and creates more space, more dark energy appears. The total amount of dark energy in the universe increases as the universe grows. This creates a feedback loop. More space means more dark energy, which drives faster expansion, which creates even more space. The result is exponential acceleration. The expansion gets faster and faster with no apparent limit. This has dramatic implications for the future. Several candidates have been proposed for dark energy. The simplest is Einstein's cosmological constant, which represents a constant energy density inherent to space itself. Space has energy simply by existing, and this energy drives expansion. Another possibility is a field called quintessence, a dynamic field that fills space and drives acceleration. Unlike the cosmological constant, quintessence could change over time, strengthening or weakening. Some theories suggest dark energy isn't a substance at all, but indicates that our understanding of gravity needs modification on cosmic scales. Perhaps general relativity breaks down at very large distances, and what we attribute to dark energy is actually a correction to gravitational theory. We don't know which, if any, of these explanations is correct. Current observations are consistent with a simple cosmological constant, but they don't rule out more exotic possibilities. Ongoing experiments are trying to determine whether dark energy is truly constant or whether it changes over time. The accelerating expansion driven by dark energy determines the universe's long-term fate. Let's trace the timeline into the distant future. Right now, we can see about 2 trillion galaxies. Over the next 100 billion years, most of these will disappear from view. The accelerating expansion will carry them beyond our cosmic event horizon, the boundary beyond which their light can never reach us no matter how long we wait. Galaxies within our local group, bound together by gravity, will remain visible, but everything else will vanish. The Milky Way and Andromeda will likely merge in about 4 billion years, forming a larger elliptical galaxy. A few dozen other nearby galaxies will also remain visible, but that's it. The sky will go dark. In about 1 trillion years, the last stars in our galaxy will burn out. Star formation will cease because all the gas will have been incorporated into stars or expelled. The galaxy will contain only dead stellar remnants, white dwarfs, neutron stars, and black holes. By 10 to the power of 14 years from now, most stars will have been ejected from galaxies through gravitational encounters. Planets will have been flung into interstellar space or swallowed by stellar remnants. Around 10 to the power of 40 years, most matter will have decayed or been pulled into black holes. If protons are unstable, they'll have decayed. Planets, moons, asteroids, all the solid matter we know will have disintegrated. By 10 to the power of 100 years, even black holes will have evaporated through Hawking radiation. Stephen Hawking showed in the 1970s that black holes slowly radiate particles and lose mass. Larger black holes take longer to evaporate, but even supermassive black holes will eventually disappear. After 10 to the power of 100 years, the universe will be a cold, dark, nearly empty expanse. All that remains is a thin mist of photons, neutrinos, and a few elementary particles spread across an ever-expanding space. The temperature will be incomprehensibly close to absolute zero. Entropy will have reached maximum. Nothing interesting can happen anymore because there's no energy gradient to drive any process. This is called heat death, and it represents the most likely end state of the universe based on current understanding. Not an end in the sense that the universe ceases to exist, but an end in the sense that nothing can happen. The universe reaches a state of maximum entropy where time becomes meaningless because nothing changes. Heat death assumes dark energy remains constant. But what if it doesn't? If dark energy strengthens over time, the acceleration could become so extreme that it tears apart structures held together by gravity. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems. Eventually, even planets would be ripped apart. Continue this process, and eventually even atoms themselves would be torn apart as space expands faster than forces can hold particles together. This is called the Big Rip, and calculations suggest it could occur perhaps 20 billion years from now if dark energy behaves this way. Current observations suggest this isn't happening, but we can't completely rule it out. Alternatively, what if dark energy weakens or reverses? If the cosmological constant isn't actually constant, if it decreases over time, gravity might eventually overcome the expansion. The universe would stop expanding and begin contracting. As contraction accelerates, galaxies would collide and merge. The cosmic microwave background would shift from red to blue as space contracts, becoming hotter and hotter. Eventually, everything would merge back into a hot, dense state similar to the Big Bang but in reverse. This is called the Big Crunch. Some models suggest the Big Crunch could trigger a new Big Bang, creating an oscillating universe that cycles through expansions and contractions forever. But current observations show no sign of this. The expansion appears to be accelerating, not slowing. We've established that the universe is probably infinite, or at least unimaginably vast. But what does infinite really mean? It's not just a really big number. It's something categorically different, and our intuitions about finite quantities fail us completely. Mathematicians have rigorously studied infinity for over a century. In the late 1800s, Georg Cantor developed set theory and discovered that infinity has surprising, even paradoxical properties. Consider a simple example. Take the set of all positive integers, 1, 2, 3, 4, and so on forever. This set is infinite. Now, take the set of all even integers, 2, 4, 6, 8, and so on forever. This set is also infinite. Which set is larger? Your intuition might say the integers are larger because they include all the even numbers plus all the odd numbers. But Cantor showed they're actually the same size. You can match them up 1 to 1, 1 matches with 2, 2 matches with 4, 3 matches with 6, and so on. Every integer gets matched with exactly 1 even number, and every even number gets matched with exactly 1 integer. The sets have the same cardinality, the same size of infinity. This seems wrong. How can a set be the same size as a subset of itself? But that's exactly what characterizes infinite sets. They can be put in one-to-one correspondence with proper subsets of themselves. Here's another example that illustrates the strangeness. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, and so on forever. Every room is occupied. A new guest arrives. Can you fit them in? In a normal hotel, you'd say no, we're completely full. But in the infinite hotel, you ask every guest to move to the next room number. The guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on. This frees up room 1 for the new guest. Now imagine infinitely many new guests arrive, each needing a room. Can you accommodate them? Yes, ask every current guest to move to twice their current room number. Guest in room 1 moves to room 2, guest in room 2 moves to room 4, guest in room 3 moves to room 6. This frees up all the odd-numbered rooms, which are infinite in number, for the new guests. You've added infinite guests to infinite guests and still have room. Infinity plus infinity equals infinity. This violates our intuitions about addition, but it's mathematically rigorous. Cantor discovered something even stranger. There are different sizes of infinity. The set of integers is infinite. The set of real numbers, including all decimals and irrational numbers like pi, is also infinite. But Cantor proved the real numbers are uncountably infinite, a strictly larger infinity than the countable infinity of integers. You cannot match up the real numbers with the integers 1 to 1. No matter how you try, there will always be real numbers left over. The set of real numbers is in some precise mathematical sense more infinite than the set of integers. Some infinities are bigger than others. This has implications for an infinite universe. If space is continuous and infinite, it contains uncountably many points. If it's quantized at the Planck scale and infinite, it contains countably many discrete regions. The type of infinity matters. If the universe is spatially infinite, and matter is distributed roughly uniformly, something remarkable follows from basic probability theory. Every possible configuration of matter must occur somewhere, and not just once, but infinitely many times. Here's why. Consider a region of space the size of the observable universe, about 90 billion light-years across. Within that region, there are roughly 10 to the power of 80 particles. These particles can be arranged in different ways. The number of possible arrangements is stupendously large but finite. Calculations suggest maybe 10 to the power of 10 to the power of 120 different configurations. That's a number so large it's hard to fathom. Write the number 1, then write 10 to the power of 120 zeros after it. It's far larger than the number of atoms in the observable universe, larger than any number you encounter in daily life. But it's still finite. Now, if the universe is infinite and roughly uniform, there are infinitely many regions the size of the observable universe. Each region contains particles in some configuration. Since there are infinitely many regions, but only finitely many possible configurations, every configuration must repeat. This means there are infinitely many regions exactly identical to our observable universe. Not similar, but identical down to every atom, every arrangement, every person, every thought. Somewhere, incredibly far beyond our horizon, there's another Earth exactly like this one, with another you reading this exact sentence at this exact moment. And not just one copy, infinitely many copies, infinitely many Earths, infinitely many versions of you, all existing simultaneously in different parts of infinite space, all having identical experiences right now. There are also infinitely many regions that are almost identical but with small differences. Another Earth where you chose coffee instead of tea this morning. Another where you pursued a different career. Another where you were never born but everything else is the same. Every possible variation exists somewhere. In fact, every possible arrangement of matter exists somewhere. Solar systems with different numbers of planets, galaxies shaped differently, civilizations more advanced than ours, civilizations that destroyed themselves. Every possible configuration, every possible history, all playing out in different regions of infinite space. This isn't speculation. It's a direct mathematical consequence of an infinite universe with uniform properties. If space goes on forever and contains matter, everything that can happen must happen infinitely many times. We can never verify this. These duplicate regions are beyond our cosmic horizon, unreachable by any means. The expansion of space ensures we'll never contact them, never see them, never know their specific locations. For all practical purposes, they might as well exist in separate universes. But if the universe is infinite and uniform, they must exist. Infinity creates strange problems for physics and cosmology. One of the most disturbing is the Boltzmann brain paradox, named after 19th century physicist Ludwig Boltzmann. In an infinite universe, or even in a very large finite universe, random thermal fluctuations can create any structure, including brains. It's incredibly improbable, but in infinite space with infinite time, improbable things happen. Here's the problem. It's much more probable for a random fluctuation to create a single disembodied brain with false memories of a past that never happened than to create an entire universe with a consistent history leading to that brain. By simple probability, most conscious observers in an infinite universe should be Boltzmann brains, random fluctuations with no real past, rather than actual people who evolved through cosmic history. This leads to an absurd conclusion. You're more likely to be a Boltzmann brain with false memories than a real person. Your memories of childhood, education, everything you think you've experienced, are more likely to be false, created by a random fluctuation moments ago. This is clearly ridiculous, but resolving the paradox is tricky. Various solutions have been proposed. Maybe the universe isn't truly infinite in time, so there isn't enough time for many Boltzmann brains to form. Maybe quantum mechanics prevents such fluctuations. Maybe we're using probability wrong in infinite contexts. The Boltzmann brain paradox illustrates a deep problem. Infinity combined with probability creates paradoxes. In a finite universe, you can calculate probabilities by counting outcomes. In an infinite universe, standard probability theory breaks down. This leads to what cosmologists call the measure problem. In a finite universe, calculating probabilities is straightforward. Count how many times something happens. Divide by the total number of trials, and you get the probability. But in an infinite universe, this doesn't work. If there are infinitely many observers, and infinitely many of them see outcome A, while infinitely many see outcome B, what's the probability of seeing A versus B? Infinity divided by infinity is undefined. You might think the answer is 50-50 if half see A and half see B. But in infinite sets, half is ambiguous. You can match every observer who sees A with an observer who sees B and still have infinitely many of both left over. Cosmologists need some way to compare infinite sets, some measure that weights different regions of infinite space. Various proposals exist. Maybe you weight regions by their volume, maybe by the number of observers they contain, maybe by how probable they were to form. Different measures give different predictions. And we have no way to know which measure, if any, is the correct one. This is an active area of research where mathematics, physics, and philosophy intersect. The measure problem reveals a fundamental tension. Science relies on probabilities to make predictions. But if the universe is infinite, standard probability might not apply. We might need new mathematical frameworks to do cosmology in an infinite universe. Quantum mechanics adds another layer of strangeness to infinity. In standard quantum mechanics, particles exist in superpositions, being in multiple states simultaneously until observed. Observation collapses the superposition to one definite state. But the many worlds interpretation proposed by Hugh Everett in 1957 suggests observation doesn't collapse anything. Instead, the universe splits into branches, with each possible outcome occurring in a different branch. If you measure a particle that could be spin up or spin down, the universe branches into two, one where you observe spin up, another where you observe spin down. Both outcomes happen, just in different branches of reality. Both versions of you exist, each having observed a different result, each convinced they're in the one real universe. If many worlds is correct, the number of branches is enormous. Every quantum measurement in the entire universe causes branching. The decay of a radioactive atom creates a branch where it decayed and another where it didn't. Every photon hitting a detector creates branches for all possible detection outcomes. Every interaction between particles creates branches. Over cosmic time, this creates an unimaginably vast number of parallel realities, possibly infinite if quantum events continue forever. Each branch is a separate universe with its own history. Some branches are nearly identical to ours, differing only in the outcome of a single quantum event somewhere. Others differ dramatically, having made different quantum choices at every step since the Big Bang. Consider a simple example. A uranium atom has a half-life of about 4.5 billion years. This means it has a 50% chance of decaying in that time. In many worlds, after 4.5 billion years, there are two branches, one where it decayed, another where it didn't. After another 4.5 billion years, each of those branches splits again, creating 4 branches total. Now, scale this up. The universe contains about 10 to the power of 80 particles. Many of these participate in quantum events constantly. The number of branches grows exponentially with each event. After just a second, the number of branches is incomprehensibly large. After billions of years, the branching structure is infinite, or close enough to make no difference. Each branch is a complete universe with its own history, its own galaxies, stars, planets, and observers. In some branches, dinosaurs never went extinct. In others, humans evolved differently or never evolved at all. In some, you made different choices at key moments in your life. Every possible quantum history is realized in some branch of this vast tree of parallel realities. Many physicists find many worlds elegant because it takes quantum mechanics seriously without adding extra mechanisms like wave function collapse. The Schrödinger equation, which describes how quantum states evolve, naturally produces superpositions. Many worlds simply says these superpositions are real. All outcomes happen. We just find ourselves in one particular branch. But many worlds is controversial precisely because it's unfalsifiable. We can never observe other branches by the very nature of quantum mechanics. The branches are separate, unable to interfere with each other once they've split. This puts many worlds in a strange position, mathematically elegant and consistent with quantum mechanics, but impossible to test. Still, many worlds illustrates how infinity appears even in the quantum realm. If it's correct, reality is vastly larger than what we observe, with infinitely many quantum branches, each representing a different possible history. Probability in an infinite universe creates paradoxes that challenge our basic understanding of chance and likelihood. In a finite universe, probability is straightforward. Count the number of ways something can happen, divide by the total number of possible outcomes, and you get the probability. But in an infinite universe, this breaks down completely. If infinitely many events occur, and infinitely many result in outcome A, while infinitely many result in outcome B, what's the probability of A versus B? You can't divide infinity by infinity. The result is undefined. Mathematicians have developed frameworks for handling some types of infinity. You can talk about the density or frequency of events, even when the total number is infinite. If half the events result in A and half in B, you might say each has probability 1/2, but this requires careful definitions of what half means when you're dealing with infinite sets. The problem becomes acute in cosmology. Consider a simple example. In an infinite universe, there are infinitely many Earth-like planets. On some, life evolved. On others, it didn't. What's the probability that any given Earth-like planet develops life? You might try to calculate this by looking at our local region and seeing what fraction of Earth-like planets have life. But which region do you choose? Different regions might have different fractions. And if the universe is infinite, there are infinitely many regions to choose from. This is called the measure problem in cosmology. To make predictions, you need some way to assign weights or measures to different regions of the infinite universe. But there's no obviously correct way to do this, and different choices give different answers. One approach is to weight regions by their volume. Count how many Earth-like planets exist in increasingly large spheres around us, and see what fraction have life. As the sphere grows, the fraction might converge to some value, which you could call the probability. But this assumes the universe is roughly uniform at large scales. If different regions have systematically different properties, volume weighting might not work. Maybe you should weight regions by the number of observers they contain, or by the amount of information they could process. Different weighting schemes give different probabilities. This isn't just a philosophical puzzle. It affects real predictions. When cosmologists try to calculate what we should observe given different theories of the early universe or multiverse, they need to assign probabilities. But in infinite scenarios, Probabilities depend on the choice of measure, and we don't know which measure is correct. Some cosmologists think this means we need new mathematical frameworks for doing science in infinite universes. Probability theory, as we know it, might be inadequate. We might need different approaches that can handle infinity more naturally. Others think the measure problem suggests something is wrong with our theories. Maybe the universe isn't actually infinite. Maybe eternal inflation doesn't happen. Maybe we're missing something fundamental that would make the problem disappear. This remains an active area of research, where mathematics, physics, and philosophy intersect. The measure problem reveals fundamental tensions in trying to do science when infinity is involved. Our standard tools, developed for finite systems, might not apply. We might need new mathematics to properly describe an infinite cosmos. One of the most striking features of our universe is how precisely the fundamental constants appear to be tuned for life. Let's look at specific numbers to see just how narrow the life-permitting range is for some parameters. Consider the strength of gravity. Gravity is characterized by Newton's gravitational constant, g, which has a value of about 6.67 times 10 to the power of -11 in standard units. If g were just 10% larger, stars would burn 10,000 times faster. The sun would exhaust its fuel in about 1,000,000 years instead of 10 billion years. Complex life wouldn't have time to evolve. If g were 10% smaller, stars would burn so slowly they'd never get hot enough to produce the carbon and oxygen that life requires. The universe would be filled with cold, dim stars, unable to support life-permitting planetary systems. The electromagnetic force, characterized by the fine structure constant alpha, has a value of about 1 divided by 137. If alpha were just 4% larger, carbon couldn't form in stellar cores. Without carbon, the chemistry necessary for life as we know it becomes impossible. If alpha were smaller, nuclear fusion in stars would be less efficient. Stars would be dimmer and shorter-lived, again making it difficult for complex life to evolve. The mass ratio between protons and neutrons is 1.00138 to 1. This seems like a trivial difference, but it's crucial. If neutrons were just 0.2% lighter, they'd be stable and wouldn't decay into protons. Atomic nuclei would be all neutrons, and chemistry as we know it couldn't exist. If neutrons were 0.1% heavier, they'd decay too quickly in the early universe. All neutrons would have decayed into protons before they could combine into helium nuclei during Big Bang nucleosynthesis. The universe would be pure hydrogen with no heavier elements, making complex structures impossible. The cosmological constant, related to dark energy, has a value of about 10 to the power of -52 per square meter in natural units. This is extraordinarily small, far smaller than most theoretical predictions would suggest. If it were just 10 times larger, the universe would have expanded so fast that galaxies couldn't form. If it were negative and just slightly larger in magnitude, the universe would have recollapsed before stars could form. The amount of matter in the universe, compared to antimatter, is another fine-tuned parameter. For every billion antimatter particles in the early universe, there were about 1 billion and 1 matter particles. This tiny asymmetry, just 1 part in a billion, left us with the matter we see today after matter and antimatter annihilated each other. If the asymmetry were smaller, there wouldn't be enough matter left to make galaxies and stars. If it were much larger, it would change the dynamics of the early universe in ways that might prevent structure formation. The list goes on. The ratio of the strong nuclear force to the electromagnetic force, the number of spatial dimensions, 3 seems special for allowing stable orbits and complex structures. The initial density fluctuations in the early universe that grew into galaxies, each parameter appears to fall within a narrow life-permitting range. Calculating the overall probability of getting all these parameters right by chance is difficult because we don't know if they're independent or related by some deeper theory. But rough estimates suggest the odds are astronomically small, perhaps 1 in 10 to the power of 100 or less. This fine-tuning is one of the deepest mysteries in cosmology. Either we're extraordinarily lucky, or there's some explanation. The multiverse offers one explanation. If there are countless universes with different parameters, some will inevitably be life-permitting. The anthropic principle then explains why we observe fine-tuning. We must observe a life-permitting universe because we couldn't exist in any other kind. Others seek a deeper theory that predicts these parameters and explains why they must have life-permitting values. String theory, for instance, aims to derive all fundamental constants from a single underlying theory. If successful, it might show that fine-tuning is illusory, that the parameters must have their observed values for some mathematical reason we don't yet understand. If the universe is infinite, or even just vastly large, and if life-permitting conditions are common, then there should be countless civilizations out there. So where are they? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" In an infinite universe, the paradox becomes more acute. There aren't just many civilizations. There are infinitely many. Some should be far more advanced than us, capable of interstellar or even intergalactic travel. Over billions of years, they should have spread across vast regions of space. Yet we see no sign of them, no alien megastructures, no evidence of industrial-scale engineering, no radio signals. The universe appears empty of intelligent life, at least in our observable region. Various explanations have been proposed. Maybe life is much rarer than we think. Maybe intelligent life is common, but technological civilizations are short-lived, destroying themselves before achieving interstellar travel. Maybe advanced civilizations deliberately avoid contact. Maybe interstellar travel is harder than we imagine, effectively impossible even for advanced civilizations. Or maybe we're looking in the wrong way, or at the wrong time. Maybe advanced civilizations use communication methods we haven't invented yet. Maybe they passed through our region of space billions of years ago, long before Earth formed. In an infinite universe, even if civilizations are incredibly rare, there are still infinitely many of them. The question becomes not whether they exist, but why we don't see evidence of them nearby. Perhaps the distances are simply too vast. Even in an infinite universe, if civilizations are rare enough, the nearest one might be millions or billions of light years away, far beyond any possibility of detection or contact. So far, we've focused on our universe, the one that began with our Big Bang. But several theories suggest there might be other universes, separate from ours, each with its own space, time, and possibly different physical laws. These ideas collectively form the multiverse concept. The simplest multiverse follows from what we've discussed. If our universe is spatially infinite, then every possible observable universe, every possible 46.5 billion light-year sphere exists somewhere. In this quilted multiverse, infinitely many observable universes overlap, all part of the same infinite space. Move far enough, and you'd enter a different observable universe, though you could never travel far enough, because the expansion of space would carry distant regions beyond your reach. But there are more radical possibilities that suggest genuinely separate universes, not just distant regions of the same space. Eternal inflation provides one such possibility. Recall that cosmic inflation was a period of exponential expansion in the early universe. In the simplest models, inflation starts uniformly everywhere and ends uniformly everywhere. But in more sophisticated models, inflation doesn't end everywhere at once. Imagine inflation as a field filling space. In some regions, this field decays and inflation stops, creating a bubble of normal space. This bubble becomes a universe like ours, with its own Big Bang and subsequent normal expansion. But outside the bubble, inflation continues. Eventually, more bubbles form where inflation stops. Each bubble is a separate universe with its own Big Bang. But the space between bubbles continues inflating forever, and more bubbles constantly form. This is eternal inflation, and it creates an infinite multiverse of bubble universes. Each bubble is causally disconnected from the others. The inflating space between them expands faster than light, so no signal can pass from one bubble to another. From inside any bubble, including ours, the other bubbles are fundamentally unobservable beyond even a cosmic event horizon. Our universe would be just one bubble in an infinite foam of bubble universes, each forming, expanding, and perhaps eventually dying through heat, death, or other fates, while new bubbles constantly form in the eternally inflating background. String theory. A leading candidate for a theory of everything that would unify all forces and particles, suggests yet another type of multiverse. String theory requires extra dimensions of space beyond the 3 we experience. Current models need 10 or 11 total dimensions. These extra dimensions must be compactified, curled up extremely small. A common analogy is a garden hose. From a distance, a garden hose looks one-dimensional, just a line. But up close, you see it has a second dimension curled around the hose. An ant, walking on the hose, can move along its length or around its circumference. In string theory, 6 or 7 extra dimensions are curled up at every point in our familiar 3-dimensional space. These dimensions are so small, around the Planck length of 10 to the power of -35 meters, that we don't notice them. But here's the key. There are many ways to curl up extra dimensions. Different shapes, different sizes, different topologies. Each configuration produces a different low-energy physics in the observable dimensions. Different particle masses, different force strengths, different values for fundamental constants. Calculations suggest there might be about 10 to the power of 500 different possible configurations. Each configuration represents a different vacuum state with its own effective physical laws. This vast collection of possibilities is called the landscape. If eternal inflation is correct, different bubbles could settle into different vacuum states, different points on the landscape. Each bubble universe would have different physical laws. Our universe has one particular configuration, but other universes would have different configurations. This landscape multiverse would contain 10 to the power of 500 different types of universe, each with unique physics. Most would be sterile, unable to support complex structures or life, but some fraction would be life-permitting. We find ourselves in one of those because we couldn't exist in the others. The many worlds interpretation of quantum mechanics, which we touched on earlier, creates perhaps the strangest multiverse of all. In this interpretation, every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. The number of branches grows exponentially. Every particle decay, every quantum fluctuation, every interaction governed by quantum mechanics creates new branches. Over cosmic time, the number of branches becomes unimaginably vast. Each branch is a complete universe with its own history. Some branches are nearly identical to ours, differing only in the outcome of a single quantum event. Others diverge dramatically, having made different quantum choices at every step since the Big Bang. This quantum multiverse is fundamentally different from the others we've discussed. The other multiverses involve separate regions of space or separate bubble universes. But the quantum multiverse involves parallel realities that coexist, separated not in space, but in Hilbert space, the mathematical structure that describes quantum states. We can never observe other quantum branches. They're separate from ours by the very nature of quantum mechanics. This makes many worlds unfalsifiable, which troubles some physicists. Others argue it's the simplest interpretation of quantum mechanics, requiring no special collapse mechanism beyond the basic equations. If many worlds is correct, asking where does the universe end becomes even stranger. Does each branch have its own edge? Do they share boundaries? The questions multiply faster than answers. There's another type of edge we should consider, one that's particularly unsettling. It comes from quantum field theory and the concept of vacuum stability. In quantum field theory, what we call empty space isn't truly empty. It's filled with quantum fields permeating all of space. These fields have energy, and they settle into their lowest energy state, called the true vacuum or ground state. But what if our vacuum isn't the true vacuum? What if the fields are in a false vacuum, a metastable state that appears stable but isn't the absolute lowest energy configuration? If so, the vacuum could undergo a phase transition to the true vacuum, like supercooled water suddenly freezing. This transition would start at one point in space, creating a bubble of true vacuum. The bubble wall would expand outward at the speed of light, converting false vacuum to true vacuum as it grows. The problem is that the true vacuum might have different properties than the false vacuum. The Higgs field, which gives particles their masses, might have a different value. This would change particle masses. The electromagnetic field might have different properties, changing how forces work. Chemistry and atomic structure could be impossible. If vacuum decay occurred, the expanding bubble would destroy everything in its path, not in the sense of blowing things up, but in the sense that the fundamental laws of physics would change. Atoms would come apart. The familiar structures we know would cease to exist. There's no warning. The bubble wall moves at the speed of light, so you can't see it coming. One moment, everything is normal. The next moment, the wall hits and physics changes. You'd have no time to observe or understand what's happening. From your perspective inside the bubble, if you could still exist, the universe would simply have different laws than it did a moment ago. This sounds like science fiction, but it's a genuine possibility arising from quantum field theory. The good news is that our vacuum appears to be stable, or at least very long-lived. Calculations based on the measured masses of the Higgs boson and top quark suggest our vacuum is metastable, meaning it's stable for now, but could eventually decay. The estimated lifetime before decay is enormous, perhaps 10 to the power of 100 years or longer, far longer than the current age of the universe. We're probably safe for the foreseeable future, but we can't completely rule out vacuum decay. It represents a type of edge, not in space, but in the stability of physical law. The possibility that the rules governing reality could suddenly change, creating an expanding bubble of altered physics sweeping through space at light speed. Some thinkers have seriously proposed that we might be living in a computer simulation, that our reality is actually software running on some substrate in another reality. While this sounds like pure science fiction, it's been discussed by philosophers and even some physicists. The argument, most famously presented by philosopher Nick Bostrom in 2003, goes like this. If it's possible for civilizations to create realistic simulations of conscious beings, and if such civilizations have reasons to run many such simulations, then the number of simulated minds would vastly outnumber real biological minds. By simple statistics, you're more likely to be in a simulation than in base reality. If we are in a simulation, the universe's edge might be the edge of the simulation. Perhaps space doesn't extend beyond the observable universe because the simulators didn't bother simulating regions we can't see. Or perhaps the universe is infinite, but only observed regions are computed in detail, with distant regions generated procedurally when needed. Some have looked for evidence of a simulation. Maybe there are glitches, bugs in the code that produce unexplainable anomalies. Maybe we can find signs of the computational substrate, regularities in physics that suggest an underlying grid or discrete time steps. So far, no convincing evidence has been found. The universe appears continuous, not pixelated. Physics follows smooth differential equations, not the discrete updates of a computer program. And even if we found apparent glitches, how would we know they weren't just new physics we don't understand yet? Some thinkers have seriously proposed that we might be living in a computer simulation, that our reality is actually software running on some substrate in another reality. While this sounds like pure science fiction, it's been discussed by philosophers and even some physicists. The argument, most famously presented by philosopher Nick Bostrom in 2003, goes like this. If it's possible for civilizations to create realistic simulations of conscious beings, and if such civilizations have reasons to run many such simulations, then the number of simulated minds would vastly outnumber real biological minds. By simple statistics, you're more likely to be in a simulation than in base reality. If we are in a simulation, the universe's edge might be the edge of the simulation. Perhaps space doesn't extend beyond the observable universe because the simulators didn't bother simulating regions we can't see. Or perhaps the universe is infinite, but only observed regions are computed in detail, with distant regions generated procedurally when needed. Some have looked for evidence of a simulation. Maybe there are glitches, bugs in the code that produce unexplainable anomalies. Maybe we can find signs of the computational substrate, regularities in physics that suggest an underlying grid or discrete time steps. So far, no convincing evidence has been found. The universe appears continuous, not pixelated. Physics follows smooth differential equations, not the discrete updates of a computer program. And even if we found apparent glitches, how would we know they weren't just new physics we don't understand yet? The simulation hypothesis faces deep philosophical problems. If we're in a simulation, the computer running it exists in some reality. We can ask the same questions about that reality. Is it also a simulation? This leads to infinite regress unless there's some base level of reality that's not simulated. Moreover, even if we found evidence suggesting we're in a simulation, we couldn't be certain. Any evidence could itself be part of the simulation. The hypothesis is effectively unfalsifiable, which puts it outside science's domain. But it represents an interesting philosophical possibility for where the universe might end. At the boundaries of a computational system designed to simulate reality for purposes we can't fathom. We've focused on spatial boundaries, but the universe also has temporal edges. We know about the beginning, the Big Bang, but what about the end? The most likely fate, based on current understanding, is called heat death. The universe continues expanding forever, driven by dark energy. As expansion continues, galaxies drift apart. Stars burn out one by one. Over trillions of years, all the stars that will ever form have formed and died. Black holes remain for a time, but they're not eternal. Stephen Hawking showed that black holes slowly radiate particles through quantum effects, losing mass in the process. Larger black holes take longer to evaporate, but even supermassive black holes will eventually disappear. A stellar mass black hole takes about 10 to the power of 67 years to evaporate. A supermassive black hole, like the one at the center of the Milky Way, takes about 10 to the power of 100 years. These timescales are incomprehensible, but they're finite. After 10 to the power of 100 years, even the largest black holes have evaporated. What remains? A cold, dark, nearly empty expanse. Photons with wavelengths stretched to cosmic proportions. Neutrinos barely interacting with anything. Maybe some electrons and positrons, scattered across vast distances. The temperature is essentially absolute zero, differing by only the tiniest fraction of a degree. Entropy has reached maximum. There's no energy gradient anywhere. Nothing can happen because all processes require energy differences, and there are none. The universe reaches thermodynamic equilibrium, a state where nothing changes because there's no energy available to drive change. This is heat death. Time doesn't end in the sense that the universe ceases to exist, but time becomes meaningless because nothing happens. The universe has reached its final state, unchanging and unchangeable. This scenario assumes the expansion continues forever and dark energy remains constant. If dark energy strengthens, we might face the Big Rip instead, where acceleration becomes so extreme that it tears apart all structures. If dark energy weakens, we might face the Big Crunch, where the universe recollapses. But based on current observations, heat death seems most likely. The universe will expand forever into a cold, dark, empty future where nothing interesting ever happens again. Physicist Roger Penrose has proposed an alternative to heat death called conformal cyclic cosmology. In this model, the universe doesn't end with heat death. Instead, it cycles through infinite eons, each beginning with something like a Big Bang. The idea is subtle. In the far future heat death scenario, only massless particles like photons remain. In general relativity, for massless particles, time loses meaning. Penrose proposes that this far future state could be mathematically transformed into conditions resembling a new Big Bang, starting a new eon. Each eon goes through the same stages: Big Bang, inflation, structure formation, dark energy domination, heat death, then transformation into the next eon's Big Bang. The universe cycles eternally through these eons. Penrose even suggests we might find evidence of this in the cosmic microwave background. Events from the previous eon, particularly collisions of supermassive black holes, might leave imprints detectable as subtle circles in the microwave background of our eon. Several analyses have looked for these circles. Some claim to find them, others find no convincing evidence. The proposal remains controversial, neither confirmed nor definitively ruled out. If conformal cyclic cosmology is correct, the universe has no end, only transformations from one eon to the next. What appears to be heat death is actually a transition to a new beginning. Another alternative comes from loop quantum gravity, an approach to quantum gravity different from string theory. In loop quantum gravity, space is not continuous, but made of discrete quanta, tiny loops of space at the Planck scale. When applied to cosmology, this framework suggests the Big Bang might not be a true singularity where density and temperature become infinite. Instead, quantum effects of gravity might prevent infinite compression. The universe could contract only to a finite maximum density before bouncing back and beginning to expand. This big bounce would replace the Big Bang as the beginning of our observable universe. Before the bounce, the universe was contracting. After the bounce, it's expanding. What we call the Big Bang is actually the bounce point. If this is correct, our universe might be one phase in an eternal cycle of expansions and contractions. Or it might be a single bounce after a single previous contraction. Current observations don't distinguish between a true Big Bang singularity and a bounce, so this remains speculative. But it offers another possibility for the universe's temporal boundaries. No absolute beginning, just a bounce from a previous contracting phase. Whether there's an absolute end depends on the future behavior of dark energy and gravity. We've explored the question of where the universe ends from every conceivable angle. We've examined ancient cosmologies and modern physics. We've discussed the observable universe and the whole universe, spatial boundaries and temporal ones, the multiverse and the limits of what we can know. After all this, what can we conclude? The honest answer is that we don't know for certain where or if the universe ends. We have strong evidence for some things and educated speculations about others, but certainty eludes us. We don't know if the universe is finite or infinite. Measurements suggest it's flat, which usually implies infinite. But we can't rule out a very large finite universe that appears flat at observable scales. We don't know if there's a multiverse. Several theories suggest one, but we have no direct evidence. The other universes, if they exist, might be forever beyond our ability to observe. We don't know what dark energy is or what causes acceleration. We can measure its effects with precision, but its nature remains mysterious. We don't know whether our vacuum is truly stable or could undergo catastrophic decay at any moment. We don't know if we're in a simulation, and we probably never will because the hypothesis seems unfalsifiable. These aren't temporary gaps in knowledge that better experiments will fill. Some might be fundamental limits on what we can observe or test. If something is beyond our cosmic event horizon, we can never see it. If vacuum decay travels at light speed, we can never receive advance warning. If we're in a simulation, we might never find proof. Imagine inflation as a field filling space. In some regions, this field decays and inflation stops, creating a bubble of normal space. This bubble becomes a universe like ours, with its own Big Bang and subsequent normal expansion. But outside the bubble, inflation continues. Eventually, more bubbles form where inflation stops. Each bubble is a separate universe with its own Big Bang. But the space between bubbles continues inflating forever, and more bubbles constantly form. This is eternal inflation, and it creates an infinite multiverse of bubble universes. Each bubble is causally disconnected from the others. The inflating space between them expands faster than light, so no signal can pass from one bubble to another. From inside any bubble, including ours, the other bubbles are fundamentally unobservable beyond even a cosmic event horizon. Our universe would be just one bubble in an infinite foam of bubble universes, each forming, expanding, and perhaps eventually dying through heat, death, or other fates, while new bubbles constantly form in the eternally inflating background. Science works by observation and testing. We make hypotheses, derive predictions, test those predictions against reality. But if something is fundamentally unobservable, science can't reach it definitively. We can speculate, build mathematical models, argue philosophically, but we can't test empirically. This doesn't mean such questions are meaningless. They have answers, presumably. The universe either is infinite or isn't. There either is a multiverse or isn't. Our vacuum either is stable or isn't. These are facts about reality, even if we can never determine them with certainty. There's something both humbling and mysterious about this. Humbling because despite all our progress, we're still fundamentally limited in what we can know. Mysterious because reality might be far stranger and more complex than we can ever discover. Despite the uncertainties, we've learned an enormous amount. Let's appreciate what we know with high confidence. The universe had a beginning about 13.8 billion years ago in an event we call the Big Bang. The evidence for this is overwhelming. The expansion of the universe, the cosmic microwave background, the abundances of light elements, the ages of the oldest stars. Space itself has been expanding since the Big Bang, carrying galaxies apart. This isn't motion through space, but expansion of space itself. We've measured the expansion rate precisely and tracked how it's changed over cosmic history. The observable universe has a radius of about 46.5 billion light-years and contains approximately 2 trillion galaxies. These galaxies are gravitationally bound into groups, clusters, and superclusters connected by filaments, forming a cosmic web. The universe is flat or very close to flat, suggesting it's either infinite or extraordinarily large. Any curvature is so slight we can't detect it with current measurements. The expansion is accelerating, driven by dark energy that makes up about 68% of the universe's total energy content. Dark matter, which we can't see directly but detect through gravitational effects, makes up about 27%. Ordinary matter, everything we can see and touch, is only about 5%. The cosmic microwave background exists, filling all of space with faint radiation at a temperature of 2.7 degrees above absolute zero. This radiation is the cooled remnant from when the universe first became transparent, about 380,000 years after the Big Bang. The universe underwent a period of cosmic inflation in its first fraction of a second, solving the horizon and flatness problems and creating the density fluctuations that grew into galaxies. Physical laws appear to be the same everywhere and at all times in the observable universe. The same forces operate, the same particles exist, the same mathematical relationships hold. All of this we know with high confidence, supported by multiple independent lines of evidence. These aren't speculations. They're established facts about the universe. Understanding the universe's scale inevitably raises questions about our significance. We're unimaginably tiny. Earth is a small planet orbiting an ordinary star in a typical galaxy, one among trillions. The observable universe might be a tiny fraction of the whole. We're specks on a speck existing for a cosmic instant. Physically, we're insignificant. The universe doesn't revolve around us. It wasn't created for us. We arose on one planet through natural processes that, as far as we can tell, follow physical law with no purpose or intent. The cosmos is indifferent to our existence. But there's another perspective worth considering. We're part of the universe that has become aware of itself. Through us, the universe observes itself, understands itself, asks questions about itself. Atoms forged in dying stars billions of years ago have arranged themselves into patterns complex enough to contemplate their own cosmic origins. That's extraordinary. We're not just passive observers. We're active participants in a cosmic story of matter organizing itself into ever more complex forms until it achieves self-awareness and understanding. Yes, we're small and brief, but we're also capable of comprehending the vast and the ancient. We can look up at the night sky and understand what we're seeing. We can trace cosmic history from the Big Bang to the present. We can ask where the universe ends and make serious attempts to answer using mathematics and observation. The universe might be indifferent to our existence, but we're not indifferent to the universe. We wonder about it, explore it, try to understand it, and in doing so, we create meaning, at least for ourselves. We're the universe's way of knowing itself, however briefly. So where does the universe end? After this long exploration, we can offer an answer that's nuanced and honest. The observable universe has a boundary at about 46.5 billion light-years from Earth. But this isn't a physical edge. It's just the limit of what we can see from our location at this moment in cosmic history. Move to a different location, and the boundary moves with you. It's an observational horizon, not a wall. The whole universe, beyond what we can observe, might be infinite, extending forever with no edge. Measurements suggest this is likely, though we can't be certain. Space might simply go on forever, galaxy after galaxy, with no boundary to reach. If you could travel faster than cosmic expansion, which you can't, you could go as far as you wanted and never reach an edge because there is no edge to reach. Alternatively, the universe might be finite, but curved back on itself, like the surface of a sphere in 4 dimensions. In that case, it would have no edge either. You could travel forever in one direction and eventually return to your starting point, having circumnavigated the universe. There would be no boundary, no place where space stops. There might be other universes beyond ours in an inflationary multiverse, quantum multiverse, or landscape multiverse. Each would have its own boundaries, its own physics, its own story. Our universe might be one among infinitely many. The universe definitely has temporal boundaries. It began 13.8 billion years ago in the Big Bang. It will end in heat death, probably trillions of years from now, when it reaches maximum entropy and nothing interesting can ever happen again. These temporal edges are as real as any spatial boundary. There are boundaries of knowledge, regions beyond our cosmic event horizon that we can never observe, questions we can never definitively answer, truths forever hidden from us by the structure of space-time and the limitations of observation. The universe might have an edge of stability in vacuum decay, where the laws of physics could suddenly change in an expanding bubble moving at light speed. So the universe has edges, but not in the simple way ancient peoples imagined. Not walls or boundaries in space where things stop. The edges are more subtle. Horizons of observation, limits of causality, boundaries of knowledge, temporal endpoints, possible phase transitions in the fabric of reality. You can't point a telescope in some direction and see the edge of the universe. You can't travel to it in a spaceship. The universe doesn't end the way a country or continent ends with a border you can cross. Instead, the universe ends in infinity or in curvature that prevents edges. It ends at the limits of what we can observe and know. It ends in time at the heat death when change becomes impossible. These are the edges of everything we know. Our understanding continues to evolve. New telescopes are peering deeper into space and farther back in time. The James Webb Space Telescope is revealing galaxies that formed when the universe was only a few 100 million years old, testing our theories of structure formation. Experiments continue searching for dark matter particles. If found, it would be one of the greatest discoveries in physics, explaining what makes up most of the matter in the universe. Observations are measuring dark energy's properties more precisely. Future surveys will determine whether it's truly constant or whether it changes over time, which would dramatically affect the universe's ultimate fate. Physicists continue developing theories of quantum gravity that might reveal the nature of space and time at the deepest level. Loop quantum gravity, string theory, and other approaches might eventually be tested through observations of the early universe or black hole physics. We might detect primordial gravitational waves from inflation, providing direct evidence of the universe's first moments and revealing the energy scale of inflation. We might find biosignatures on exoplanets, proving life exists elsewhere and addressing the Fermi paradox. Or we might be approaching fundamental limits, boundaries beyond which we cannot pass with any conceivable technology. Some questions might remain permanently unanswered, mysteries that define the ultimate limits of human knowledge. But the search itself has immense value. Every discovery, every unanswered question deepens our understanding of reality. We're participants in an ongoing conversation between humanity and nature, asking questions and listening for answers, pushing the boundaries of what we know. The edge of the universe is not just out there in space. It's also at the limits of what we can observe, understand, and imagine. And pushing against those limits, trying to see a little farther, understand a little deeper, is one of the noblest human endeavors. Where does the universe end? We've journeyed from ancient cosmologies to modern physics, from the Big Bang to heat-death, from the observable universe to the multiverse. We've examined infinity and its paradoxes, dark energy and its mysteries, the limits of knowledge and the boundaries of reality. The answer is complex. The universe doesn't end in a simple way. It doesn't have a wall or boundary you could reach. If it's infinite, it has no spatial edge at all. If it's finite, it curves back on itself with no boundary. Either way, space doesn't just stop somewhere. But the universe does have horizons. The observable universe is limited by how far light has traveled since the Big Bang. The cosmic event horizon limits what we'll ever be able to observe, even if we wait forever. These aren't physical barriers, but they're real limits on what we can know. The universe had a beginning and will have an ending. These temporal boundaries are as significant as any spatial edge. The Big Bang marks the origin of everything we know. Heat-death marks the end of change and complexity. There might be other universes, creating boundaries between different realms of reality. Our universe might be one bubble among infinitely many, one quantum branch among countless others, one point on a vast landscape of physical possibilities. And there are limits to knowledge itself. Some questions might be permanently unanswered, not because we're not smart enough or don't have good enough instruments, but because the answers lie beyond what can ever be observed or tested. The edge of everything we know is not a place you could visit. It's a horizon, constantly receding as we learn more but always present, reminding us that reality is larger and stranger than what we can comprehend. Thank you for joining this exploration to the edge of everything we know. If you enjoyed it, a like and subscribe really helps the channel grow. The universe is vast, ancient, and filled with mysteries we're only beginning to unravel. Good night, and may your wonder about the cosmos never end.